Hello people, I'm Bharat Acharya. Welcome to our new video. So in today's video, we're going to learn the data transfer group of instructions of 8051 microcontroller. Now you know 8051 has 111 instructions classified into various groups. One of those groups is data transfer group. As the name suggests, data transfer group means you transfer data from one place to the other. You don't do any add, subtract, multiply, divide, no AND or XOR, nothing. The simple data transfers. Are they useful? They're probably the most used instructions in a program. You take the printout of any program, you'll see predominantly move instructions all over the place. Most of these instructions are move instructions. I'll tell you something about move instruction. When you write a move, you write two operands in the instruction, X and Y as an example. The first operand is always the destination. So the syntax goes move destination comma source. The data will be copied from the source to the destination. 1 second, what did I say? Data will be copied. There is no cut. It's just a copy. You know the difference, right? Data will remain in the source but will also get copied into the destination. Now what are these sources and destinations possibly? They could be a register, the most important register, that's accumulator. It could be any of the RAM registers. It could be direct addressing mode where you give an address. It could be indirect addressing mode where you give the address using a register. I'm sure you know that if you've seen addressing modes. That's the way you learn the subject. You first learn addressing modes, then you go into instructions, then you go into programs. Don't do it the other way around. So we have done video of addressing modes. When you learn addressing modes, you know what various addressing modes are. This is immediate addressing, register addressing, direct addressing, indirect addressing. You've seen that. So I'll be teaching you the various move instructions. Then the MoveX and the MoveC types. MoveX are for external RAM and MoveC is for ROM, internal as well as external. Now, when you use external memory, there are some typical rules that apply. All transfers are with a register, you cannot use direct addressing mode, and you can only do a data transfer. You cannot directly add or subtract. Now, there is an implication of this. If I take the same program for internal memory and for external memory, there'll be a world of a difference between the program. A program to add two numbers. So I'm going to show you the program. I won't just say it, I'll show it to you, writing instructions. If I have to add two numbers in internal RAM, it's such a small program. If I have to add two numbers in external RAM, it's going to be this big a program. Why? Because of the rules that come along with the MoveX instruction. So I'll be telling you the rules and their implication. How does it affect you as a programmer? Students in their practical exam pick up the question and they see add two numbers. They feel very happy. What is important to notice is whether the question is for internal RAM or for external RAM. For internal RAM, yes, it's your lucky day. External RAM, no, it's not that you're unlucky, but it's just that it's going to take much more effort. Working with external RAM requires a lot of skill, which is what I'm going to be showing you over here. Anyway, then we'll be seeing push and pop instructions. These are instructions related to stack operations. This comes as a 5-mark question, especially in Bombay University. It's a typical question. Explain stack related instructions of 8051. It may come directly, it may also be used indirectly. I'm sure you know there's a topic called interrupts. I'm sure you also know it's a very important topic. In the explanation of interrupts, if you know when a processor gets an interrupt, it goes to the ISR. While doing that, it does a push. It pushes the return address into the stack, and while coming back, it pops the return address. So again, there also you need to explain push and pop. So once for all, understand push and pop properly. So I'm going to be showing you that with examples. And then finally, the last part of this group, exchange instructions. They are pretty simple. The name itself is the answer. They will exchange the value of the two registers. Now, there is a typical instruction over here, XCHD. This comes a lot in the exam because many students ignore this instruction, and when they suddenly see it in the exam, they think it's a typing mistake. That D is just extra. It is supposed to be only XCH. There is an XCH with the same operands. There is an XCHD. There is a difference between the two. I'm going to be showing you that again with examples. So that's the scope of this video. Okay. So our first instruction, move a comma hash n. Please answer by yourself. What is this hash n? You've seen addressing modes. What is hash n? Hash n means a number. Any number with a hash is data. Any number without a hash is address. You remember that? So when you write move a comma hash 25, that's the example. That means a gets the value 25. Please tell me, are you clear? A gets the number 25. Put the number 64 in a register. Move a comma hash 64. Are you clear? Next, move a comma RR. What is RR? RR means RAM register. So it can be anything from R0 to R7. So who gets what? A gets the value of R0. Remember, you write the destination first and then the source. So data is copied from the source into the destination. If you've seen addressing modes, you'll find this much part redundant because you've seen it. This also, but since it's important, it's worth revising. From there onwards, the new part will start. So I'll go a little fast on this. If you've seen addressing modes, you know this. We've covered all of these in addressing modes. Move a comma address. Now what do you mean by an address? Address means a number without the hash symbol. Example, move a comma 25. This is move a comma hash 25. That is data. This is address. So when you write move a comma 25, A gets the contents of location 25. Correct? Tell me, did you understand this? Move a comma @ RP. Any register with an @ acts as a pointer. RP means register pointer. Which are the two registers which can be used as pointers? Come on. R0 and R1. No other register. So it could be either R0 or R1. So move a comma @ R0. What does that mean? Who gets what? Come on, tell me. A gets the data from the location pointed by R0. See again, A gets the data from the location pointed by R0. Suppose R0 is 20, move A comma R0, A gets 20. Move A comma at the rate R0, A gets the contents of location 20. So the value of R0, which was 20, will just act as an address. A will go to that, processor will go to that address, from there will get the data and put it into A register. So for the last time, A gets the contents of the memory location pointed by R0. That means the memory location whose address is given by R0. Tell me, did you understand this? Now, just like you had all of these options with A, then you'll have them with the registers, then you'll have them with location pointed by the register. So there are various permutations and combinations that you can have. You can have the reverse of this, you can have the reverse of this, and so on. So the whole list is there in the PDF. Check it out. I would like to write it on the board also, but there'll be like 25 instructions doing the same thing, and we have seen all of those in addressing modes. So I just want to revise this. An interesting one which I want to revise. We've seen in addressing modes, but I want to revise this. Move address 1 comma address 2. Example, move, yeah, remember we've seen this in addressing modes. Move 20H comma 30H. Both of these are addresses. This is a strange instruction. If you've learned microprocessors in lower semesters and now you come into microcontrollers, you will find this strange. This is not allowed in microprocessors, but is allowed in microcontrollers, transferring data directly from one memory location to another memory location, writing two addresses in one instruction. So move 20H comma 30H, location 20 will get the data of location 30. Contents of location 30 will be stored at location 20. Please tell me, did you understand this? Now, those were simple basic move instructions. What do you mean by move X? X stands for external RAM. Now, when you want to access external RAM, you cannot use direct addressing. You remember? You have to use indirect addressing. That means the address has to be given by a register. External RAM has 16-bit address. So ideally, you should be using a 16-bit register like DPTR, data pointer. Remember? So MOVEX A comma at the rate DPTR. What does the at the rate make you understand? That DPTR is giving an address. And what does X make you understand? That address belongs to external RAM. So A gets the data from the location pointed by DPTR in the external RAM. What does that mean? If DPTR is 2000, is A getting 2000? No. A is getting the contents of location 2000 from external RAM. Please tell me, did you understand? That caret symbol is used to indicate that it's working on external RAM. In your explanation, you can write external RAM, but if you don't want to write that much, just put that caret symbol. The symbol is called caret, C-A-R-E-T. When you put this, it indicates that it works on external RAM. Similarly, the reverse operation. MOVEX at the rate DPTR comma A. Come on, explain to me by yourself. MOVEX at the rate DPTR comma A. That means A is getting the data or giving the data. A is giving the data to the location pointed by DPTR in the external RAM. So if DPTR is 4000, the value of A will be stored at location 4000 of the external RAM. Tell me, are you clear? You've seen all of this in addressing modes. I'm not teaching this. If I was teaching this, I would go much slower. You've seen addressing modes, you know it. This is more like a revision. That part is new. MOVEX A comma at the rate R0. Now, external RAM, you know, has 16-bit address, but the first 256 locations have such addresses whose higher byte is 00. The addresses will go from 0000 to 00FF. So since the higher byte is 00, you can only give the lower byte of the address. The processor will assume the higher byte to be 0. If you remember, we've discussed this also. So if you're giving only the lower byte of address, that means you're giving only 8-bit address. 8-bit address can be given by R0 or R1. So you can use R0, R1 for internal RAM as well as for external RAM. Then how do you know whether it's internal RAM or external RAM? For internal RAM, the instruction is move. For external RAM, the instruction is MOVEX. MOVEX A comma at the rate R0. Who gets what? A gets the data from the location pointed by R0 in the external RAM. Please tell me, did you understand this? Next one. MOVEX at the rate R0 comma A. Now A is giving the data to the location pointed by R0 in the external RAM. Please tell me, are you all clear? This was done in addressing modes. Like I said, we are revising. So what's this? This was also done. Move C. MOVEX is for external RAM, move is for internal RAM, move C is for ROM, C for code memory. Now in ROM, if you remember, you use index addressing. There is a reason also for it, which again I have explained. Index addressing is useful to access lookup tables. In a lookup table, one register acts as the base of the table, the other register acts as the index within the table. Do you remember? So you initialize DPTR as the base of the table, you use A as an index within the table. Hence the addressing mode is called index addressing. Address is given as a sum of two registers. One becomes the base, the other becomes the index. So you've seen it, right? You want me? I would draw it again. The same lookup table, give the same explanation again. What's the point? You learned it. Let's not do the same thing again and again. Let's focus on things which are new. You've seen that already. That's addressing modes. Watch the video of addressing modes in case you don't remember this. I've explained this in complete detail. Move C A comma at the rate A plus DPTR. Who gets the data? A. From the location, because there is an at the rate, that means you're talking about the location pointed by A plus DPTR. Let's take an example. Let's say DPTR is 1000. Valid? A is 25. Valid? So A plus DPTR becomes 1025, 1025. A is not getting 1025. A is getting the contents of location 1025. From which memory? RAM or ROM? ROM. Now is it internal ROM or external ROM? Depends upon the address. If the address is less than 1000, it could be either internal ROM or external ROM. If the address is more than 1000, definitely external ROM, because internal ROM ends at 0FFF. We have covered all of this in the topic of addressing modes. Now, if the address is less than 1000, it could be either internal ROM or external ROM, depending upon the value of EA bar. Do you remember? If EA bar stands for external access. If EA bar is 0, what is it? Internal ROM or external ROM? Don't try to remember. Those who try to remember will forget. If you understand, you'll never forget. EA bar stands for external access. External access. Bar means active load. That means if it is 0, it is active, which means if it is 0, the location will be accessed from external ROM. If it is 1, the location will be accessed from internal ROM. Now, when will this come into picture? When the address is less than 1000. If the address is 1000 and more, definitely it will be accessed from external ROM, because there is no address 1000 and more in the internal ROM. So for the last time, if this address is 1000 or more, it is 100% working on external ROM. If the address is less than 1000, depending upon EA bar. If EA bar is 0, it will work on external ROM. If EA bar is 1, it will work on internal ROM. Same thing, instead of A plus DPTR, A plus PC, same concept. Now, I went fast, I know, because we've learned this in addressing modes. Now, something which you have to be sure of as a programmer. This is internal RAM, correct? 8-bit address. This is external RAM, 16-bit address. I'm giving you the same question for both of them. Write a program to add the contents of location 20 and 21, store the result at 22. Similarly, add the contents of 2000, 2001, store the result at 2002. Now, on the face of it, both are same programs, adding 2 locations, storing the result in the third location, correct? But the way you're going to tackle it depends completely upon whether it's internal RAM or external RAM. The approach changes completely. Internal RAM, very simple. Take the data from 20 into A, add the data of 21, answer will come in A, store the result at 22. Come on, give me the instructions. Come on, 1, 2, 3, 3 instructions. Come on, come on, come on. Take the data of 20 into A. Move A, 20H. Add the data of 21. Add A, 21H. Answer comes in A. Store that answer at 22. Move 22H, A. So simple. When you're working with internal RAM, life is very easy. Now, when you're working with external RAM, there are 3 problems that you need to understand. First, there is no scope of direct addressing. So everywhere where you wrote addresses is not going to work. You have to use indirect addressing, which means first of all, you will need to initialize DPTR with 2000 so that you can access this location as the location pointed by DPTR. Then for the subsequent locations, you need to go on incrementing DPTR so that you can access those locations. So do you understand? A few instructions will be added in the program. First of all, initializing DPTR, then subsequently incrementing DPTR for every location. So 3 instructions. So abhi samajh mein aa gaya that they'll be added in your program. Now, I'll tell you more. When it comes to external RAM, you cannot do this. What did I do here? In internal RAM, we directly added the number to A. That is not possible. You have add. You don't have addx. You have only movex. That means after taking this first number into A, you cannot directly add this number to A. You will have to again first take this number and then add it to A. So this won't be 1 step, it will be 2 steps. In fact, it won't even be 2, it will now be more for the third problem. What are the first 2 problems? First, you cannot use direct addressing. Second, you cannot directly add. You have to do a movex and first get the number. Third problem, all transfers with external RAM happen only via A register. I am 8051, you are external RAM. I want data from you, I can only get it into A register. I want to send data to you, I can only send it via A register. The gateway into 8051 is A register. Once the data comes in A, you can transfer it wherever you want to, but it will come or will go only via A register. That means you will first take the first number in A. You ideally want to add this number, you can't. So you will take the second number. Now what you would want to do is take the second number into some other register and then add these 2, but that's not possible. The only register in which you can get this number again is A, which means after taking the first number, you have to transfer into some register like R0. There is an abundance of registers. It's not that you're going to fall short of registers, but the number of steps are increasing. So take the first number in A, transfer into R0, take the second number in A, now add A in R0. Answer will come in A, store that answer at location 2002. That too again not by direct addressing, by going on incrementing DPTR to access. For every location that you want to access, you need to increment DPTR. So once I'm going to tell you all the steps, then you are going to tell me the program. If you can tell me the program, that means you have understood the points that I'm trying to make. What are the 3 points? You cannot directly add subtract, you cannot use direct addressing, and you can only transfer data using A register. Now, let me tell you the sequence of steps, then you'll frame the program. Initialize DPTR with 2000. Take the data pointed by DPTR into A, transfer the data from A to R0, increment DPTR so that it points to 2001, take the new data pointed by DPTR into A, add A with the value of R0, which means the previous data, answer will be in A, increment the value of DPTR so that it points to 2002, Store the value of A at this new location pointed by DPTR. Come on. You think you can dictate the instructions? Have full confidence. Come on. Have confidence in yourself. You know it. At the most, what will happen? You'll forget move X and say move. Or you'll forget an @ That's all that will happen. But you'll more or less give me the same correct answer. 1 or 2 mistakes are fine. That's how we learn. If I'm going to teach you how to cycle, you cannot expect to learn it without falling even once. If I teach you how to swim, you cannot learn it without getting water all over your nose. It is going to happen in the beginning. But if you're scared of it and you don't even try, you'll remain where you are. You keep trying, you'll make these small mistakes, and before you realize, you'll master it. Okay? So that's what I want you to do. Get the fear out and try. Come on, give me the first step. Initialize DPTR with 2000. Come on, initialize DPTR with 2000. Move DPTR, comma, hash 2000. Why hash? I don't want contents of location 2000 to come into DPTR. I want DPTR to be 2000. If DPTR is 2000, then I can use it as a pointer to get the data into A register. Please tell me, did you understand this? So right now DPTR is 2000. Now using this 2000 as a pointer, get the data pointed by DPTR. That means get this data into A. Come on, instruction. Move X, A, comma, @ DPTR. Did you forget to say X? It's okay. You will not make this mistake again. Why is this a move and why is this a move X? Here you're putting a number into DPTR. You're not doing anything to external RAM. You're just initializing DPTR. Here you are getting data from external RAM. So this is a move X. Please tell me, did you understand? So what happened is data came into A. Now from A transfer into R0. Tell me, from A transfer into R0. Come on. Move, shabash, move R0, comma A. Will this be a move X or a move? This is a simple move. You're not transferring anything from any external memory. You're transferring from a register to a register. It's a simple move. Are you clear? Good, you're getting a grip on it. Now increment the value of DPTR. Simple. Increment DPTR. Now take this new data pointed by DPTR into A. This time no mistake. Take the data pointed by DPTR into A. Come on. Move X, shabash, move X, A, comma, @ DPTR. So you got your second number into A. Now add A and R0. Add A, comma, R0. Answer comes in which register? A. You want to store it at 2002, but you can't do it directly. First, you need to increment DPTR. Increment DPTR. Now, come on, last instruction. Come on, my sake, last instruction. Store the value of A at this location pointed by DPTR. Think about it and give me the full instruction. Store the value from A at the location pointed by DPTR. Come on, instruction. Move X @ DPTR, comma A. You're storing the value from A to the location pointed by DPTR in the external RAM. This is a move X because you're transferring into external RAM. This is move X, this is move X, this is move X. The others are normal instructions. So move X, and move X. Please tell me, are you clear? What did you understand from this? What did you understand? Same question. When you're working with internal RAM, it's a hell lot easier. When you're working with external RAM, because of the 3 rules that I said, you cannot use direct addressing, you cannot work on any other register other than A, and you cannot directly add subtract. You have to first get the data and then do whatever you want to do. Because of those rules, that same program of 3 instructions will become 1, 2, 3, 4, 5, 6, 7, 8 instructions, almost 3 times the size. So that's what I'm saying. When you get a question in the exam, watch out which memory is being used. If nothing is being mentioned, it's your choice. Obviously, you'll do it with internal RAM. But if they have said external RAM, then you've got to understand how to use external RAM. So this was the first one. As you do more and more programs, you'll get more and more comfortable with it, no doubt. Now, stack-related operations. There are only 2 stack-related operations by the names, obvious names, push and pop. When you say push, you want to put something into the stack. You know that, right? You know what's a stack, right? This is a stack. There are how many elements in the stack right now? 3. The first element, they're entered. Second element, last element. So the stack works in the principle last in, first out. Push, pop, pop, pop. Are you clear? Push means put something in the stack. Pop means remove it from the stack. Now, look at it. When you say push 25, so first thing you have to know, push only supports direct addressing mode. Nothing else works. It only works in direct addressing mode. That means the only thing you can write over here is an address. No other entity. Not A, not a register, nothing else. The only thing you can write over here is an address. So an examiner says, push the number 33. Students write, oh, so simple. Push hash 33. No, you can't do that. First put that 33 into some location. Let's say location 20. So move 20, hash 33 and then write push 20. You can only push the contents of an address. You cannot directly push a number into the stack. Is that clear? So push 25. What are you pushing? 25? No. You are pushing the contents of location 25 into the stack. Please tell me, did you understand? Now this is your internal RAM. If your basics are clear, if you watch the video of structure of internal RAM, you know the default value of SP is 07. Please tell me you remember all this. I would love to explain the whole logic again. What's the point? We can't keep learning the same thing again and again, right? If you watch the videos, if you've seen the initial video structure of internal RAM, you know this point. So SP by default is 07. Whenever you do a push, SP has to get incremented, which means your first data will come at location 08. This is garbage. Your first data will come over here. What are you trying to push? Contents of location 25. Whatever is stored over here will be pushed over here, and now this will become the new top of stack. SP will be pointing to that location. So that means there are 2 things that have to happen over here. SP has to become SP plus 1 so that it points to this location, and you want to take the data of location 25 and store it over here. So can you see there are two steps? This is one, this is another. There are two steps that are taking place. All you need to tell me is what is the sequence, what will happen first. Think about it. If you want to go home and by heart the answer, it's okay. If you want to never by heart and still write, I'm not boasting. I know the whole instruction set. I teach 10 processors, so I know every instruction of every processor. That's about 1000 instructions. It's humanly impossible for a person to by heart all of them. The reason why I write all of this so fluently without even giving a second thought to it is because I've understood it. So that's why I tell students, understand things. Don't try to mug them up. You'll make a mess. But you understand it, even in half sleep, you'll be able to. We've been shooting since morning. In any state, no matter how tired you are, you'll get the correct answer if you understood it. So here is my question. You want to store the value of 25 at this location and you want SP to become SP plus 1. What should happen first? First, you will store the data or first you will increment SP? First, you will increment SP because this address is given by SP. I am the processor. You tell me do a push. I need to know where should I push. That address is given by SP. So if you directly push at the address given by SP, you'll end up pushing over here. These are stack elements. Assume this is the top of stack pointed by SP. Assume this is SP. I tell you do a push. You're not going to push here. This is the existing top of stack. You need to first increment SP so that it points to a blank location. That's where you will do your push operation. Please tell me, did you understand this? Did you understand this? Yes, the first thing that you will do is first increment SP so that it is ready to point to a blank location and then do your push operation. So your first step is SP will become SP plus 1 at the new location pointed by SP. That means at this location, we are going to store what? 25 or contents of 25? Contents of 25. So first SP will become SP plus 1, then at the new location pointed by SP, we'll store the value of 25. This was your push operation. Please tell me, did you understand this? Now if you did, explain to me pop by yourself and come on, be serious now. Pop. What do you mean by pop? Pop means remove the data from the top of stack and store it at the place that I have specified. Push 25 means push the contents of 25 into the top of stack. Pop 25 means pop the data from the top of stack and store it at location 25. Please tell me, did you understand this? Pop the data from the top of stack and store it at location 25. Pop the data. This is 07, this is 08. Suppose we had done some push, that means this is the top of stack. Suppose immediately after this push we are doing a pop. So this is SP, this is the existing top of stack. Pop this data, store it at location 25. That's what pop 25 means. Pop the data from top of stack and store it at location 25. Now once this data has been popped out, this becomes the new top of stack, which means SP should now become SP minus 1. So again, if you notice, there are two steps taking place over here. SP becoming SP minus 1 and data being removed from top of stack and stored at location 25. So now you have to answer what should happen first. This is the top of stack. I want to pop this data, store it at location 25 and SP has to become SP minus 1. What should happen first? Should I change SP first or should I pop first? Pop first. Tell me, did you understand this? Because if I change SP, that means it will point to this location. You'll never be able to access this top of stack at all. Please tell me, did you understand? When you do a push, you first increment SP so that it points to a blank location. That's where you do your push. But if you want to do a pop, you first pop the data and then decrement SP so that it points to the new top of stack. Please tell me, did you understand? Understand it. You'll never have to by heart it. That's the idea. This subject is built on logic. That's the most beautiful part about the subject. Everything is logic. Get a grip of that logic. There is no by hearting. You can master the subject. But you got to get the grip of the logic and you have to have that appetite for it, for understanding things, not mugging up. Mugging up is always the easier route. People think it's difficult, it's the easier route, but it's so boring. You understand things, that's why you took engineering, right? Anyway, pop the data from the top of stack, store it at location 25. Once you've popped it, SP will become SP minus 1. So pop the data from top of stack. That means from the location pointed by SP, pop the data, store it at location 25, and then SP will become SP minus 1. Please tell me, did you understand? Whew, that was your question pop. It's a typical 5-mark question in Bombay University. Now, last part, very easy, super simple. The name itself is the answer. Exchange instruction. Exchange A and register. Come on, come on. After explaining this, don't expect me to explain this. There's nothing in it. Exchange A and a register. We'll interchange the value of A in that register. If A was 20 and the register was 40, A will become 40, the register will become 20. As simple as that. So you can exchange A with a register, you can exchange A with the contents of an address. So exchange A comma 25, there's no hash 25, okay? Exchange A comma 25, you're exchanging the value of A with the contents of the location 25. So this location's data will come into A and A's data will go to that location. Of course, it happens internally via temporary registers, not shown. If you're learning a very basic processor like 8085, you learn how this happens using WZ pair, but it's not shown over here, so we don't even discuss. I don't want to invent things by myself, but obviously it's common sense, it's done using internal temporary registers. It can't happen by magic, that value is not going to remain in air. It has to be stored somewhere temporarily. Now, exchange A comma now. Pay attention on these two. Exchange A comma at the rate R0. First of all, understand this and explain to me. You are exchanging the value of A with the contents of the location pointed by R0. You understand? R0 points to a location. In that location, there is some data. That data and A will get interchanged. Are you clear? Exactly same operands, but the instruction is not exchange. It is exchange digit. The D stands for digit. Exchange digit. It's the same two parties, A and the location pointed by R0, but you're not exchanging their full values. You're only exchanging one digit. Which digit? The lower nibble. If the number is 25, 5 is the lower nibble. That is the digit that we're talking about. So lower nibble of A will be interchanged with the lower nibble of the location pointed by R0. Are you clear? Let's see the difference between these two. Okay, this is important. This is a repeated question in the exam because, like I said, it's very rarely used, but it exists. Students tend to ignore it. Most people think this is a typing mistake. It's not. It's a perfectly valid instruction. Look here. Suppose A is 25 and at the rate R0. At the rate R0 means location pointed by R0 is 74. Case 1, case 2. If I write exchange A comma at the rate R0, what will happen? The full numbers will be exchanged. That means A will become 74 and at the rate R0 will become 25. The full numbers will be exchanged. But on the other hand, if I just wrote this, exchange digit A comma at the rate R0, only the lower nibbles will be exchanged. That means A will become 2 will remain as it is, only 4 and 5 will be exchanged, so A will become 24 and at the rate R0 will become 75. Please tell me, did you understand? That wraps up the whole data transfer group. 1 minute recap, what do you have? The normal move instructions. The only interesting one to know is you can directly move between two memory locations. Of course, it's direct addressing mode, so it applies only to internal RAM. So move 30, 40, you will transfer the data from location 40 to location 30 as an example. When you work with external memory, what's the rule? You can only use indirect addressing, you can only transfer data using A register, and you can only do data transfers. You cannot directly add, subtract, you can only transfer the data. Push and pop. When you do a push, first SP increments, then you put the data. When you do a pop, first you pop the data, then SP decrements. Exchange, all normal exchanges. Exchange D means exchange digit. Only the lower nibbles will be exchanged. That was the data transfer group. I hope you understood it and I hope you enjoyed learning it. All the best. Do well. Hello people, I'm Bharat Acharya. Welcome to our new video. So in today's video, we're going to learn branch instructions of 8051. We've been doing the whole instruction set of 8051. I've told you there are 111 instructions. One by one, we've been covering all of them. So you've seen data transfer instructions, arithmetic instructions, logic instructions, Boolean instructions, and bit operations. And now the very big group called branch instruction. It has 21 different instructions. What these instructions do, they cause a branch in the program. See, programs normally execute in a sequential manner. Why? Because of gravity? No. Because after every instruction, PC goes on getting incremented. What is PC? Program counter. It always gives the address of the next instruction. So the address, I'm the processor, this is the memory. For me, any location in the memory can carry an instruction. I can fetch an instruction from anywhere. So the register PC, inside the processor there's a register called PC. Whatever address it gives, processor will fetch instruction from that address. Now as a principle, the moment any instruction is fetched, PC gets incremented. That is why program goes in a sequential manner. So that's the sequential flow, the default way a program works. But you've done programs in various languages. I'm sure you've done programs. You come across an if, you come across a goto, a for loop, a while loop, etc., a function call. These cause a branch in the program. So the instructions that cause a branch in the program form the branch control group. That's what we are learning. The idea of causing a branch is to change the value of PC. Otherwise, PC goes on getting incremented. When you change the value of PC, you're changing the course of the program. Now, branches are of two main types. There's something called a jump and there's something called a call. The difference between the two, in a jump, you take a jump to a new location and you continue. You forget where you come from, you don't care where you come from. You just take a jump and you go ahead. Whereas, when you do a call, you're calling a function. A function is also called subroutines in assembly language. So you're calling a subroutine. So you call a function basically. You go to the function, execute it, but you don't stay there. You come back. See the difference. In a jump, you just go ahead and continue. In a call, you call a subroutine, execute it, and come back. I'm going to teach you what are the various types of jumps. I have done a whole video. I'm sure you've seen the playlist. I've done a video on the difference between short jump, long jump, and absolute jump. I'm not doing that again in this video. What's the point of teaching the same thing again and again? That is a theory topic, the three types of jumps, short, long, and absolute. It's a fabulous topic. In Bombay University, it comes as a short question of 10 marks. Okay, it's a very, very intricate topic. I've done a separate video for that. I'm not doing that right now. I'm teaching the instructions. So there are three types of jump, short, long, absolute. There are two types of calls, and there are two types of returns. Why do you need a return? When you call a subroutine, you execute the subroutine. As I said, you don't just stay there. Then you come back. Now you won't come back by magic. There has to be an instruction for that. So the instruction is called return. It will surprisingly always get you back to the very next instruction. Of course, how does this work? I'm going to teach you in full detail. There is a role of stack in this operation, so I'm going to teach you that. Then we'll come to the conditional jumps, the one that I use much more often in programs. So there's something called CJ and E. It has various types. There's something called DJ and Z. The most important instruction of all of them in terms of usage, in terms of programming. Every loop in 8051 is made using DJ and Z. This is like your for loop instruction. So I'm going to teach you that, the various types of DJ and Z. Like we mentioned about looping, so I'm going to show you how to make loops. First we'll make an infinite loop, then we'll see various examples of finite loops. I've kept the space empty, I'm going to write all of that. And then there's a superb Viva question.
how to generate 256 iterations using an 8-bit register. I don't know which question you'll get in Viva, which the subject is huge. It's anybody's guess what can be asked to you. But if you get this question and you are able to answer this, you have won your battle with the examiner. You impress the examiner. If somebody gives this answer to me when I'm taking a Viva, you really know, yeah, okay, this student knows the subject properly. Because this is not an answer that you find in textbooks. This is an answer which either you've got to really think hard and get it, or you've done a lot of programs. That's when you realize it during programming. So anyways, I'm going to teach you how to get 256 iterations. Then there are more conditional jumps: jump if carry, jump if no carry, jump if zero, jump if no zero, indirect jump using A plus DPTR, and then bitwise jump instructions, JB, JNB, and JBC. JNB is, if you've seen theory topic of 8051, if you've seen programs related to timers, related to serial ports, you know how important this instruction is. It's there in every serious program of 8051. It's the one that is used to check whether the timer has overflown or not, or whether your serial data has been completed, and so on. Okay, so let's start. First, I'm going to make you understand what's the difference between a jump and a call. Then we go ahead. You know the different types of jumps. I'm not doing that right now. Different types are short, long, and absolute. It makes no difference to the programmer whichever jump he or she uses. The difference is only the range. In short, your range is -128 and +127. I hope you remember that. In absolute, the range is 2 kb but within the same page. And in long, the range, there's no restriction. You can jump anywhere. So we're not doing the difference between short, long, and absolute. What you need to first understand is what's the difference between a jump and a call. Look here. In a jump, you take a jump to a new location and continue. In a call, you're calling a function, a subroutine, executing it and coming back. So this is a detailed diagram of call. To go to the subroutine, you use call instruction with the name of the subroutine. I've given this the name sub, it can be any name. And come back, you use the instruction called RET. RET stands for return. Where will return get you back? To the same instruction or to the next instruction? Exactly to the next instruction. Obviously, if you come back to the same instruction, we'll end up going there again and we'll just come in finite loop. So you come back to the next instruction. Now, let's call this address return address, basically the address of the next instruction. Let's see how does this program function. Processor is executing the program sequentially by going on incrementing to PC. Few simple questions. PC stands for program counter. PC always contains address of the next instruction. The moment any instruction is fetched, PC gets incremented. Remember all these words, they will all be useful in a matter of minutes. So when processor comes to this instruction, first of all it will fetch this instruction. Now as soon as this instruction is fetched, PC gets incremented, which means PC at this point of time is containing the return address. Had this not been a branch instruction, had this been a normal instruction, after this, by normal action, PC would have gone to the next instruction and program would have followed the sequential flow. But now, because we have written call, program has to go to this subroutine. To go to this subroutine, the address of the subroutine will be put into PC. What did I say in the beginning of the video? Branching means changing the value of PC. Instead of PC containing return address, PC will now get the address of the subroutine. So the course of the program will change. We will go to the subroutine, execute the subroutine again how? Randomly or sequentially? Sequentially by going on incrementing PC, we reach here. Now, on return, program has to come back. To come back, again we are changing the flow of the program. That means again we are changing the value of PC. Now PC has to get the return address. Did you understand this point? To go to the subroutine, PC needs the subroutine address. To come back, PC needs the return address. Now for 1 minute, think you are 8051 and try to do this procedure. Immediately you will realize there is a problem, and the solution to that problem will make you understand this whole instruction. Come on, let's do it together. To go from here to here, there is no rocket science involved. Just go on incrementing the value of PC. To go from here to here, you are 8051. You want the subroutine address so that you can put it into PC. That address you will get from the instruction, because we have very clearly written call subroutine. We not just written call, we have said call subroutine. When you write subroutine, basically the assembler will substitute the address. That address will be put into PC. Program will go to the subroutine. Again, to come from here to here, there is no big deal, just go on incrementing PC. Problem happens here. See what you have written. Come on, look here. You've written RET. RET stands for return. Means all you have said is go back. What have you not told? Where to go back? Did you understand the point? In a C program, to call a function, you write the name of the function. Again, what is a name? Address. For the layman, it's a name. For a person who really understands stuff, it is an address. So while calling a function, you're giving the address. While coming back, you're just using a closing bracket. That closing bracket tells you go back to the main program, but it doesn't tell you where to go back. So that closing bracket is your return instruction. Looking at return, the processor knows it has to go back, but it doesn't know where. But it needs the return address so that it can put it to PC. You can't just put anything into PC and come back over here. You need this exact return address. So do you understand there is a problem? There is no return address provided over here. Students say, so what's the big deal? Just like you've written call subroutine, you can also write return at so and so address. Can you do that? No. Why? Because this is a subroutine. Why do we write subroutines? So that we can call them from here, from here, from here, from here, from here, anywhere. Wherever you call this subroutine from, the address of the subroutine is the same. But the return address is not the same. The return address depends upon where it was called from. That means inside the subroutine, you cannot write the return address. Did you understand the point I'm making? Inside the subroutine, you can only say return. You cannot say where to return. So there is a situation over here. Processor sees it has to return, but it has no damn clue where to go. How does it get this return address? Let's see. When the processor was doing this instruction call, what did I say? The moment this instruction was fetched, PC got incremented. That means at that point of time, PC had the return address. Does 8051 need this return address? Yes. When? Now or later? Later. While going or while coming back? While coming back. But while going, it has to put the subroutine address into PC. Now, do you understand? The moment it puts the subroutine address into PC, it will lose the return address. Do you understand that? Should it lose the return address? No, because after this return address is not provided by anybody. So what the processor does is, it sees it's a call instruction. There is a difference between a jump and a call. In a jump, you just go. In a call, you have to come back, and the processor knows that. So before putting the subroutine address into PC, it will secure this address, the return address which is there in PC right now. It will just save it somewhere. Where will it save it? The stack. Processor will push the value of PC into the stack. What has been pushed? The return address. This is your stack. This is the top of stack pointed by SP. I hope you know all of these things. You cannot start watching big videos before seeing the basics. All this is covered a long time back. So there is something called as a stack. In the stack, there are various elements. This is the top of stack. This is empty area. The top of stack is pointed by SP. So what will the processor do? It will push the value of PC. PC means return address. It will push this return address into the stack. It will come at the top of the stack, and SP will now point over here. Please tell me, do you understand this? SP gets incremented on every push. We've discussed all of this earlier. So now SP will point over here. Your return address has now been secured in the stack. Now, very conveniently, processor will put this subroutine address into PC, will go to the subroutine, execute the whole subroutine. At the end, when it encounters return, it knows it has to go back. Where does it have to go back? At that return address. Where is that return address? The stack. It will get this return address back from the stack by doing a pop. It will do a pop PC from the stack, will get back the return address, put it into PC, and that's how it will come back to the main program. Please tell me, did you understand this? Let's discuss this orally without a diagram. Come on, look here. Don't try to sneak in. Try to see what is written behind me. Come on, be honest. What was going on? Subroutine or main program? Main program. What instruction did we write? Call. Moment processor sees call, it knows it has to go and also come back. When call instruction was fetched, PC already gets incremented. That means PC is containing the return address right now. First of all, processor will push this value of PC into an independent structure called the stack. This return address has been stored in the stack. Now, into PC, processor will put the subroutine address which is written in the instruction. From there, it will now go to the subroutine, execute the subroutine. At the end, when it encounters return instruction, it wants this return address back. Where is it present? Stack. It will pop it from the stack, put it back into PC. That's how it will come back to the next instruction and will continue. Please tell me, did you understand this? Is the working of a call clear? So when we do a call, internally there is a push. When we do a return, internally there is a pop. On a call, you push the return address in the stack. On a return, you pop it back from the stack. Please tell me, be clear? This is how every function is executed, even in C language, in any language in the world. When you invoke a function, you want to execute the function, but you also want to come back to the next instruction. So when you invoke a function, the return address is stored in the stack. While coming back, it is popped back from the stack. There are various rules over here that you have to remember, but not for the sake of these instructions. So I'm not going to go too much into it. This is general knowledge. When you are inside the subroutine, you may want to push your own data in the stack also. The stack is available to the programmer. Yes, go ahead. Do as many pushes as you want, but see to it that you do the same number of pops. Look here. Look at my fingers. Think of my fingers to be stack elements. This is the top of stack. Okay. At this place we have stored the return address. The processor has stored the return address. These are empty elements. Now, during the subroutine, if you've done a push, see to it that you also do a pop. If you've done 2 pushes, do 2 pops. If you've done 3 pushes, do 3 pops. Otherwise, suppose you've done 3 pushes and only 2 pops. Your number is above the return address and is now the top of stack. On return, when the processor will do a pop, it will get back this number, and instead of coming back here, processor will go back to some random location. That should not happen. So there is a simple rule. During a subroutine, number of pushes should be equal to number of pops. It's a very simple rule. Every programmer knows when he or she is writing a subroutine, programmer knows how subroutines work. So they have to take care of this. I just mentioned this because while learning, you may get it out. In the class when I teach the students get it out. Been teaching for 18 years, so I know where my students go generally. From the experience. So in case you had this doubt, just wanted to get the solution for it. In case you have another doubt, why was this return address stored in the stack? Of all places in the world, why did we use the stack to store it? Stack is a beautiful principle, last in, first out. If you store 1, 2, 3 in the stack, you get back 3, 2, 1. So how is that useful? That is useful in the case of nested subroutines. You get a call, you go to the subroutine. Midway, you call one more subroutine. Midway, you call one more subroutine. So you pushed return address 1, then return address 2, then return address 3. While coming back, you don't want to come back in that order. You want to come back in the reverse order. All the 3 times while coming back, there will be just a return written. On that return, processor will do a pop. Now it should get back the correct return addresses. You store 1, 2, 3, you will obviously get back 3, 2, 1 because that works in the principle last in, first out. That is why return address is always stored in the stack. I hope you understood this. So that was your call instruction and return instruction. Call has 2 types, ACALL and LCALL. As I said, there's no difference between ACALL and LCALL in terms of working. It's basically the range. And this return is used to come back now. There is another return called RETI. RETI is called return from ISR. Say again, return from ISR. If you learn theory of 8051, you know this is also the way interrupts work. You know there is something called interrupts. Please tell me you know that. Now when there is an interrupt, program goes to a subroutine, that is the ISR, executes it, and then comes back to the next instruction. How does it manage to come back? Again the same thing. While going to the ISR, it will push the return address in the stack. While coming back, it will pop. So a read and a RETI practically do the same thing. A read will also pop the return address, a RETI will also pop the return address. The difference is, when you write RETI, it is assumed you're writing it for an ISR. If this was an ordinary subroutine, see, get this clear. All ISRs are subroutines, correct? All subroutines are not ISRs. There can be ordinary subroutines and there can be ISRs. Ordinary subroutine, you write read. ISR, you write RETI. What's the difference? While going to an ISR, now I'm speaking only about ISRs. While going to an ISR, all this happens. Moreover, all interrupts are disabled. This is the principle of interrupts. I have explained this in the topic of interrupts. Please check out the video. I would love to explain everything again. But you know what's going to happen? You'll keep talking the same things and miss out on the more important things that are pertaining to this topic. I have explained this point in detail in the lecture of interrupts. And it's already there on the website and on the app. Please check it out. So, when you go to an ISR, as a standard practice, interrupts are disabled. There is an EA bit in the IESFR, the MSB bit of that SFR. That EA bit becomes 0, so globally interrupts are disabled. While coming back, you want interrupts to be re-enabled. So when you write RETI, not only will it return, it will also re-enable the interrupts. That's the speciality of RETI. So if you write only RET, you will simply return. If you write RETI, you will return as well as re-enable interrupts. So RETI is written for ISRs. Okay, that's the difference between the two. So with this, what we have done are basic jumps and calls. Now, they are very important from theory point of view. You can get them as a 5-mark question, especially call and return. You may get it in 2 ways. You may get a direct question, explain call and return. Less likely, more likely, explain how subroutines are executed. That's the way they ask in Bombay University, whichever university you are in. So, you may get it that way also. Explain how subroutines are invoked, or explain the role of stack in execution of a subroutine, etc. You know, examples, they can twist the way they want the question. The answer is pretty much the same. Now, what we're learning are a list of conditional jumps from here to here. All of them are conditional jumps, different types of conditional jumps. So there's something called CJNE. Not used very often. Yes, it is used. Matrix keyboard program is a classic example where it is used. I have done that program, the video for that is also there. Check it out please. So it's not a very frequently used instruction, but yes, when required, it is a very useful instruction. CJNE stands for compare and jump if not equal. Say it again, compare and jump if not equal. So what will it do? It has three entities, x, y and the label where you want to jump. It will compare x and y. If they are not equal, it will jump to the location called label. So if you write CJNE x, y, label, first thing it will do is compare x and y. If they are equal, program will simply go ahead to the next instruction. For that, do we have to do anything great? No. By default, PC gets incremented, so program anyways would have gone to the next instruction. So this instruction will do nothing if x and y are equal. If they are not equal, program will take a jump. Hence the name compare and jump if not equal. If they are not equal, x and y are not equal, program will take a jump to the location called label. Are you clear? Let's take examples. There are four types of CJNE. CJNE A, hash 25, label. Come on, explain this to me. CJNE, compare and jump if not equal. It will compare A with the number 25. If A is not equal to 25, program will take a jump to the location called label. Otherwise, program will simply go to the next instruction. Did you understand this? Now, similarly, there are more types. Explain them by yourself. CJNE A, 25. Now, is there a difference between hash 25 and 25? Yes, I'm sure you know that. This is data 25, this is location 25. So if A, it will compare A with the contents of the location 25. If A and contents of location 25 are not equal, program will take a jump to the label. Otherwise, it will go to the next instruction. CJNE R0, hash 25. It will compare any register. It could have been any register over here. I've just written R0 as an example. So it will compare that register with the value 25. Again, the same thing. And this will compare @R0 means that you know that, right? You know what is @R0. Please watch addressing modes before you learn instruction set. Don't watch videos randomly. In the classroom, obviously, we teach in that sequence. And that's the way you've got to learn. You can't learn this before you know addressing modes. Only then you know what this instruction is. So CJNE @R0, hash 25 will compare the location data of the location pointed by R0. If R0 is 30, it will compare the contents of location 30 with the value 25. Again, if they are not equal, it will jump to the location label. Otherwise, you will go to the next instruction. Did you understand all of these instructions? So what does CJNE do basically? This is how they ask for university. They don't give the full instruction. Obviously, that's because it makes it easy. This is how it is asked as a 2-mark question. Explain CJNE x, y, z or x, y, label. It will compare x and y. If they are not equal, program will jump to the location label. Otherwise, you will go to the next location. Simple. Next. DJNZ. Very, very frequently used instruction. Practically every loop of 8051 is made using this instruction. Okay. If you've done serious programs in college, you come across this instruction lots of times. DJNZ stands for decrement and jump if not 0. I'm going to teach it with a full example because it's a very useful instruction. DJNZ, count, label. So DJNZ stands for decrement and jump if not 0. It will decrement this count. This count can be any register or it can be any memory location. So it will decrement that count and keep doing it till the time it's not 0. If decrement and jump if not 0. So it will decrement the count. If it is not 0, it will jump to the location label. Do one more iteration. Decrement the count. If it is not 0, jump to the location label. Keep doing this. The moment it becomes 0, it will not jump. Not jump means it will simply go to the next location and break the loop. So this is the instruction that makes the loop. If you want to do a loop of 5 iterations, give a count of 5. You will get first iteration, it will become 4, 3, 2, 1, 0, loop breaks. The 5 iterations are over, loop breaks and you go ahead. I'll be showing you with examples, don't worry. The count can be either in a register or in a memory location. Most people keep it in register. This is just in theory, yeah, this instruction exists. In 18 years of teaching, I've never seen a situation where you need this. You will need this when you run out of registers. Come on, 8051 has 32 registers, R0 to R7 4 times. No, at least at a student level, you will never write a program where your 32 registers are occupied. Anyway, so you never use this instruction, but it is there. You cannot be choosy when you learn instructions. Know every instruction, okay? You get a 10-mark question where they ask you 5 instructions. If you know the instructions, each instruction got 2 marks, takes 2 minutes to do. 10 marks, 10 minutes, job done. Anyway, and these are questions that give you full marks. So know every instruction, but being a teacher, it's my job to tell you what is useful, what is not. I have never seen the use of this instruction, but yeah, that very much exists. It will be used when, I can tell you the use though, it will be used when your registers are over, but they never are over, there are so many registers. This is very popular. You keep your count in some register and go on decrementing it till the time the register becomes 0. Now, since we're talking about loops, I'm going to show you how to create a loop. For that, I need to move the camera this side of the. So, we are learning how to create loops. Loops, you know, if you've done programs, you need loops a lot in programs, if you've seen programs. So first we are learning how to make an infinite loop, okay? You need it. There are various programs that need infinite loops. Suppose this is a program. I put a label back. This is the section which I want to do in a loop. I write jump. With jump, it can be short, long, absolute. That is not our concern. Our concern is that it's an unconditional jump, okay? It can be short, long, absolute. The difference is just how far this distance is. So I use any kind of jump, let's say short jump. The point is it's an unconditional jump. So jump to the location back. So what will happen? Program will come up to here, will jump to back. Then again will come down, again will go back, again will come down, again will go back. And this will end up becoming a loop. But what kind of loop? This will end up becoming an infinite loop. Why? Because you have not put any condition. An unconditional jump causes an infinite loop. Please tell me, did you understand this? Are infinite loops useful? Yes. Suppose you're making a program for a digital watch, which you want to put outside your college as a clock. Okay, come by this time, and you can skew it the way you want. Anyway, so you want to make a program for a watch. What do you need? 3 registers, an hours counter, minutes counter, a seconds counter. Initialize all of them with 0, go on incrementing the seconds counter. When it reaches 60, make it 0, increment the minutes counter. When it reaches 60, make it 0, increment the hours counter. When it reaches 24, make everything 0. One day is over. That's your program. Now, will the next day be any bigger? No, be the same. So all you need to do is put this program in a loop. When should the loop stop? After 1 week? No. After 1 year? No. After your 4 years of engineering? No. It should go on as long as possible. So that means that program is an infinite loop. Just giving you an example. There are numerous examples. Okay. So this is how you make an infinite loop, by writing an unconditional jump to a backward location. Are you clear? Now, what are more useful? Of course, finite loops. That's the one. That's the one you have to learn properly, okay? I want your full concentration here. If you know how to create a loop, you know how to write big programs. All big programs are small programs put in a loop. Get this clear. A program to add 100 numbers is the same program as to add 1 number. Add 1 number, put it in a register, put it in a loop with a count of 100, you added 100 numbers. Transfer 1 number, put it in a loop with a count of 100, you transferred 100 numbers, and so on. Okay? You want to do sorting, compare 2 numbers in the correct order, leave them, do not exchange them. Put in a loop into another loop. You sort, 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 and finish. Your sorting program is over. So the whole idea of big programs is to put a core into a loop. So if you know how to make loops, you know how to write serious programs. Okay? Look here. And it's very easy. It's a big thing, but it's very easy. Suppose this is a program. This is a section which you want to do again and again. I've written a label by the name back. You can keep any name to a label. I've kept the name back. Suppose I want to do this loop 5 times. So I keep my count 5 inside some register. Move. Some register, comma, #05H. You can use any register you want. Give me the name. Give me some register. First register that comes to your mind. Say something. A, bad choice. That's why I wanted you to say it. If you said A, bad choice. Don't feel bad if you make a mistake. Keep ego aside when you're learning. Okay? If I make a mistake, I'm a student, and if I make a mistake, I feel happy because that means I was thinking something wrong. Henceforth, I will not repeat that mistake. That's how you learn. That's how you refine your ideas. Never keep your count in A. Why? It's not like a rule. There's no book saying that. It's not rule. It's our experience. If you keep your count in A, you have blocked A register. Do understand, all adds, all subtracts, and or etc., multiply, divide, they all work on A register. A is your biggest tool in programming. How can you waste A register in holding the count? It's not like you cannot do it, but it is stupid. You block your most important register, your trump card. If you're playing chess, you lost your queen in the first move. That's it. What do you do after that? Anyway, so all I'm trying to say is don't waste A register in such unnecessary things. Okay? You need A to be free. Otherwise, all you'll do inside the loop is nothing because every instruction practically needs A. Anyway, so don't use A. Give me another register. R0. Okay, nothing great. Don't use R0, R1. These are things no textbook teaches you. These are things which experience teaches you. You don't have it, but I have it. I'm sharing it with you. Get a benefit from that. R0, R1 are the only registers that can be used as pointers. When you use something as a pointer, your idea is to access a series of locations in a loop. So you understand, if you're making a loop, in all probabilities, you want to access a series of locations. So in all probabilities, you need R0, R1 over there. If you waste R0, R1 in holding the count, how are you going to make them use as a pointer? You have abundant registers in 8051. R2 to R7, 4 times. There are 4 banks. There is no shortage of registers. Just use them diligently. Don't waste A in unnecessary things and avoid using R0, R1 unless you really need them. Okay? For simple basic stuff, use other registers. Keep these trump cards available with you when you need them. Okay, so I as a habit never use A, and to keep as much as possible avoiding using R0 and R1 where I can avoid them. So I'm keeping the register R7. You can use any register you want to. There are so many registers. So I've kept the count in R7. At the end of the loop, decrement R7. So what will happen if it was 5? It will become 4. Next time 3, next time 2, next time 1, next time 0. When it becomes 0, you should finish your iterations. So you'll be writing JNZ. JNZ stands for jump if not 0. I'm not finishing it. This is how loops were made in 8085. When Intel made 8085, their first marvelous product, This is how they used to make loops. Then they realized every loop requires these two instructions. Decrement a count and then jump if not 0. Decrement a count and jump if not 0. So if every loop requires these two instructions, why waste time with the programmer in writing two instructions? Why not create a smarter instruction that will do both the things? D, J, N, Z, R7, comma back. DJNZ. DJNZ stands for decrement and jump if not 0. What will it do? It will decrement R7. If the value is not 0, it will jump to the location back. Let's see. First iteration, R7 was 5. It will become 4. 4 is not 0. It will jump to back. Next iteration, 3, not 0, jump to back. Next iteration, 2. Next iteration, 1. Next iteration, 0. Now it has become 0. I said decrement and jump if not 0. But it has become 0. It will not jump to back. If it will not jump, then what it will do? Just sit there? No, it will go to the next instruction. By default, program goes to the next instruction. That means it will do your iterations and come out. How many iterations did it do? I've given a count of 5. Look at these lines. These lines are your iterations. Your first iteration count became 4, 3, 2, 1, 0, the loop breaks. That means you did this section 5 times. Did you understand this? You give a count of 5, you get exactly 5 iterations. Let's take one more example. Suppose this is a program. I want to do this section 8 times. I've put a label by the name back. What do? Move R7, comma, hash 08H DJNZ R7, comma, back. Show me. What will happen? First iteration count will become 7, 6, 5, 4, 3, 2, 1, 0. The loop breaks. Exactly 8 iterations. So did you understand how to make a loop? Come on, look here without looking at the board. This is a program. You want to do this part again and again 9 times. Give a count of 9 inside some register. Where will you do it? Inside the loop or outside? Yeah, let's not be stupid. You'll give the count outside the loop. If you give it inside the loop, it will always be 9. So outside the loop, give your count in some register like R7. Do your whole iteration. At the end, write DJNZ R7, comma, back. Back is the place where you start the loop from. First iteration count will become 8, 7, 6, 5, 4, 3, 2, 1, 0. Loop will break. Exactly 9 iterations. I think I made my point clear. So if you give a count of 7, you get 7 iterations. You give a count of 25, you get 25 iterations. 94, you get 94 iterations, and so on. Are you clear? So what did you understand? Bigger the count, more is the number of iterations. I'm coming to a very important question. Before that, did you understand how to make a loop? Good. You'll need it. You'll need it in practice. After you do add 2 numbers, all serious programs that you do, you'll require loops. Okay? So you know how to make a loop. Now my question is, as you increase the count, you increase the number of iterations. Your count is in an 8-bit register. R7 is an 8-bit register. What is the biggest count you can give? An 8-bit register can hold a max value of FF. FF is 255. Listen carefully. FF is 255. So if you give a count of 7, you get 7 iterations. If you give a count of FF, you get FF iterations. FF is 255. Okay, not 256. 0 to FF are 256 numbers. FF is 255, like 0 to 5 are 6 numbers. But 5 is not 6, 5 is 5. So if you give a count of 5, you get 5 iterations. If you give a count of FF, you get 255 iterations. Did you understand this? As I said, as you increase the count, you increase the number of iterations. The biggest count is FF. That will yield 255 iterations. So here is your Viva question. How do you generate 256 iterations? There are examiners, I go for Viva. Examiners know there are some questions which very few students can answer. Which are those students who have read the whole book, the textbooks, who have really slogged it out, or who have done a lot of programs. And some knowledge you get from books, some knowledge you get just by doing programs. Lots and lots of programs automatically reveal interesting facts to you. There are a lot of things I've learned from programs, which is not there in any book. Anyway, so coming back. So here is the question. They know these questions can be answered only by a few students. If you answer this, you impress the exam, you bowl them over. How do you produce 256 iterations? If you're preparing for GATE exam, very important question. How do you produce 256 iterations? I said, your register is an 8-bit register. An 8-bit register can have a max value of FF. FF is 255. So if I initialize R7 with the value FF, it can't be bigger than FF. If I initialize R7 with FF, I get only 255 iterations. I want 256 iterations. When I ask the student a question in the class, some students say, sir, do this section once again. How is that even an answer? Then do it 256 times only. Why making a loop? Using this loop structure, produce 256 iterations. How are you going to do it? Give a count of 0. That's the answer. Unbelievable, but true. Initialize your R7 with the value 0. If you give a count of 5, you get 5 iterations. If you give a count of 3, you get 3 iterations. If you give a count of 0, will you get 0 iterations? No, how can you get 0 iterations? You give an account of 0. You are still doing 1 iteration. Before you do any check or anything, you're still doing 1 iteration. So your 1 iteration is over. Then what is it? So read it. It's not JNZD. It is DJNZ. What does that mean? Full form. Decrement and jump if not 0. First it will decrement, then it will check. Do you understand that? So it will decrement R7. It won't check R7 first. It will first decrement R7. R7 was 0. When you decrement 0, it becomes -1. -1 in 2's complement form is FF. I've done this in various videos before. Okay. So when you decrement 0, it becomes FF. Like if you increment FF, it goes to 0. So vice versa. Decrement 0 becomes FF. FF is not 0. Not 0 means it will go back. Now R7 is FF. So from now onwards, you will get FF iterations. FF is 255, but it already had finished 1 iteration. That means it will produce 256 iterations. Please tell me, did you understand this? It's so crazy. It just blows your mind. As you increase the count, you get more iterations. But the biggest number of iterations surprisingly come with a count of 0. Please tell me, did you understand? So once again, count of FF will give you 255 iterations. Count of 0 will give you 256 iterations. Count of 1 will give you 1 iteration, not 257. It will give you 1 iteration. Please tell me you understand that, right? If you give a count of 1, you do 1 iteration, decrement, it will become 0. I said decrement and jump if not 0, but it's already 0, it will break the loop. So it will give you only 1 iteration. So the max number of iterations that can be produced are 256. Please tell me, are you clear? And that using an 8-bit register, of course. And that is possible by giving a count of 0. Anyway, so I'm just keeping what was there initially, but just gave you the answer. Please tell me, is this clear? Now, just a handful of instructions remaining. This was the most important instruction of the whole board, okay, in terms of usage, in frequency of use. Out of all of them, you use this the most. JC, JNC, very obvious instructions. If 8051 is the first processor you're learning, yeah, you need to know these instructions. If you learned any other processor, you come across them. They're so popular. JC stands for jump if carry, JNC stands for jump if no carry. They're typically used after add programs. When you do addition or subtraction, there is a carry or a borrow. For that, you use JC and JNC. So very typical instruction. JC label, it'll check the carry flag. If carry flag is 1, it'll jump to the location label, otherwise it'll go to the next location. JNC will again check the carry flag. Jump if no carry. No carry means if carry flag is 0, it will take a jump, otherwise we'll go to the next location. That's very simple. After this, we'll be doing programs, videos on programming. You'll be seeing programs of add. You will see this instruction. Definitely not just add, you'll see it in quite a few more programs also. Anyway, JZ, JNZ. Just like JC checks whether there is a carry or not, JZ checks whether the answer is 0 or not. But there's a difference. JC and JNC work on the carry flag. JZ and JNZ don't work on the 0 flag. There is no 0 flag. They work on accumulator. Say again, they work on what? Accumulator. So JZ label, it will check A register. If A register is 0, JZ means jump if 0. So if A is 0, it will jump to label. If A is not 0, it will go ahead. Similarly, JNZ, jump if not 0. If A is not 0, it will jump to label, otherwise we'll go to the next instruction. So basically the difference between JC, JNC and JZ, JNZ is these two check the carry flag, these two check accumulator. Jump, this is not a conditional jump. It's a very rarely used instruction also, but it exists. As I said, don't be choosy. There are so many instructions I teach. I teach more than 1,200-300 instructions. I've not done a rote count. But out of that, I know there are good 200-300 instructions out of all the processors, which are very, very rarely used. And some of them I've never seen their use in all these years of teaching. But still, they still exist. They've been made to be used someday or the other in some situation or the other. As a student, you don't come across them. So you'll never really come across a situation where you need to use this instruction, but still it exists. Jump at the rate A plus DPTR. PC will get the value of A plus DPTR. So program is taking a jump to a location whose address is not given by one register, it's given by a sum of 2 registers, A plus DPTR. So DPTR plus A together will give a number, that number will be put into PC, program will take a jump to that location. Please tell me, are you clear? Now, Bombay University 5-mark question. Exactly this title. Explain bitwise. Bitwise is also called Boolean. Explain Boolean conditional instructions. These are also conditional jumps, but they are Boolean, which means they check a bit. JB, jump if bit. Such a common mistake. JC is jump if carry. Some students very innocently, JB jump if borrow. No, my friend. Carry and borrow are the same thing. For borrow also, you basically check the carry flag. So there's no instruction called jump if borrow. JB stands for jump if bit. JB bit label, that's the syntax. So if this bit can be any bit. I've given an example of P0.3. You know SFRs are bit addressable. There are bit operations in 8051. So if P0.3, jump if bit means 1. So if P0.3 is 1, program will take a jump to the location down. Otherwise, we'll simply go to the next location. Please tell me, are you clear? This is your program. You've written JB PSW.4, skip. If PSW.4 is 1, program will take a jump to the location skip. Otherwise, we'll simply go to the next location. Please tell me, are you clear? So it's checking a single bit. That's why it's called bitwise conditional instruction. It can be any bit of any register, whichever is bit addressable, of course. A, B, PSW, P0, P1, P2, P3, SCON, TCON, IE and IP are bit addressable. Okay, so out of those registers, it can check any bit and go to that location based on whatever location you've written. So that is JB, jump if bit. JNB, jump if not bit. Not bit means not set. Not set means 0. So if some bit is 0, program will jump to the location label. Example If you've seen timer programs, you know you use this instruction a lot. Okay, JNB. TF0, timer overflow flag. I'm not teaching timers over here. Don't mix two topics. I'm just using that as an example. So TF0 is timer overflow flag. So J and B, if that jump, if not bit means 0. If TF0 is 0, jump to wait. 0, jump to wait. 0, jump to wait. So you've created a loop. Is it an infinite loop? No. There is a condition. If this bit is 0, jump here. So the moment this bit becomes 1, the loop breaks. So this is how you do timer programs. You give your count, you give your mode, you start the timer, and then you keep looping. Wait for the timer to overflow. When this bit becomes 1, this loop automatically will break and program will go ahead. So very useful in timer programs. Even in serial port programs, same thing. You decide serial port mode, you do all the time programming, you put your data in SBUF register, go on transmitting, wait for TI to become 1. So this is an instruction which has big use in complex programs of timers or serial port, etc. So for the last time, JNB X comma label. What does that mean? If this bit is 0, program will take a jump to location label. That label can be anywhere, it can be on the same instruction also, just as I've given an example. So if this bit is 0, program will go there, otherwise it will simply go to the next location. Then, last one, JBC, the last instruction of all the 21, big video, yeah? I thought it would be a small one. JBC, jump if bit and clear. Say again, jump if bit and clear. Some people also say jump if bit and complement. Means the same thing. Okay, so you can treat it the way you want. Now look here, in this context it means the same thing. I'll explain to you. JBC, don't look at C right now. Just look at JB. What is JB? Jump if bit. So if this bit, don't look at C. JB, P0.7 comma down. So if P0.7 is 1, only then program will take a jump to location down. Tell me, do you understand that much? Now what is JBC? It's a double action instruction. It'll do two things. Not only jump if bit and clear. So only if this bit is 1, program will take a jump to location down, and while jumping will also clear the bit. Did you understand? Two actions. So when you encounter this instruction, P0.7 could be either 0 or 1, correct? Jump if bit. So if P0.7 is 1, only then it will perform the jump, and while jumping will also make this bit 0. Please tell me, did you understand? If P0.0 was 0, it will do nothing, it will simply go to the next instruction. If this bit was 1, it will jump, and while jumping will clear the bit. You can also say complement the bit, because it was 1, you complement it becomes 0, you clear it becomes 0. So in this context, JBC can be said as jump if bit and clear, or jump if bit and complement. Different textbooks, different full forms, means the same thing. Please tell me, did you understand? So that was your whole branch control group. Let me just revise them. You have basic jumps, short, long, and absolute. You have basic calls, you have return. In a call, there is a push. In a return, there is a pop. You have ordinary return, and you have reti. The only difference is in reti, you also enable interrupts. You have conditional jumps like CJ and E. It will compare two numbers. If they are not equal, only then it will jump. You have DJ and Z. It will decrement a register. If it is not equal to 0, it will do the jump. So it is used to create a loop. Infinite loops are made using unconditional jumps. Finite loops are made using DJ and Z. I've taught you how to produce 256 iterations. Then basic conditional jumps which are there in every processor. Carry, no carry, 0, no 0. The only thing is it doesn't check the 0 flag, it checks accumulator. For carry, it checks the carry flag, of course. Jump at the rate A plus DPTR. Program will take a jump to the location whose address is given by a sum of two registers. So it will do DPTR, let's say is 1000, A let's say is 25, it'll add the 2 becomes 1025. Program will take a jump to location 1025. PC will get 1025. Boolean conditional instructions, so they are used to check individual bits of registers. JB will jump if the bit is 1, JNB will jump if the bit is 0, JBC will jump if the bit is 1, and while jumping will make the bit 0. Please tell me, are you clear? That's the whole conditional or the branch instructions of 8051. See ya.